welcome to section 6.3. Today we're going to continue talking about rational equations, all those fractions we've been dealing with in this unit, but we're specifically going to look at their graphs today. Alright, so a rational function, we already know, is basically a fraction where we take one kind of expression and divide it by another one. Okay, we've been doing that so far, but today we're going to focus on their graphs, and we've seen these before. Okay, we've talked about asymptotes, and we kind of seen these show up on our graphs before. We're going to take a look at what's called a slant asymptote today. Okay, this is an example of a slant asymptote where we kind of have it going at an angle instead of just up and down, the vertical one, or even this horizontal one. So rational equations, nothing new that we've been already doing, just today we're going to focus on their graphs. One thing we can do with rational equations is find their domain, okay, specifically graphically what x values will work or which ones do not work. Kind of remember at the beginning of the year we had two things that might happen when we're dealing with these fractions. We could have some holes in our graph, but we could also have some asymptotes. So those holes are the removable pieces where we're going to go through some examples just to refresh our memory, but we are specifically able to remove factors from our equation. So holes on a graph kind of look like a regular graph, but there's just kind of a piece or a chunk missing. Okay, this is an example of a hole. Whereas the vertical asymptotes are the non-removable ones. They're kind of the leftover pieces if we can't remove them. But vertical asymptotes are this dotted line that kind of separates two pieces of our graph. So we might have something that looks like that, how they're separated. So let's take a look at some of these examples of our rational equations and find the domain. Specifically, since we're talking about fractions, we know the bottom cannot be 0. So in order to help us figure that out, let's factor what we can first. In the denominator, we can take out a 2x, and we're left with an x minus 4. Now, specifically looking at our denominator, we know our x values cannot be 0 from this piece, but it also cannot be 4 from this one. So to determine which of these pieces are vertical asymptotes, which ones are holes, maybe they're both holes, maybe they're both vertical asymptotes, we want to see, can we simplify our fraction any further? We'll take a look at our numerator of x minus 4, and there is a common factor in the denominator, which means those cancel out. So all we're left with is a 1 over 2x. Now notice how we were able to remove this factor. Okay, it's gone, it's no longer in our problem or our equation. So this x value of 4 that came from those factors would be a hole. Okay, we were able to remove those factors. It was a removable chunk, which is a hole. But this 0 came from the x, which is still in our problem, which means this would be a vertical asymptote. Hopefully we kind of remember doing those at the beginning of the year at some point. Moving on to the next one, let's try to focus on our denominator. We know x squared plus 4 cannot equal 0. But notice how if we tried to solve this, okay, if we were to subtract 4 over and then take the square root of both sides, we would have plus or minus 2i. Okay, this is an imaginary number, okay, meaning it's not real. So if this is a imaginary number, it's not real, okay, we're not getting an answer really to this problem. So our domain in this case would be all real numbers because we specifically don't have a real value. Okay, 0 and 4 were real values over here, but this one is not. So in this case we have all real numbers. Now, checking out our next one, kind of simple. X plus 1 cannot equal 0. So x cannot equal negative 1. We can't really factor the top to help us cancel anything out. So if this x plus 1 cannot cancel with anything up top, this specific value is going to be a vertical asymptote. We were not able to remove it like we were over here with the x minus 4. So a little refresher from the beginning of the year, we're definitely going to be needing these in this section when we talk about graphing these rational functions. Alright, so something else we can find in order to help us graph rational functions are the x and y intercepts. So if you think about a graph, Okay, an x-intercept is any point that touches the x-axis. So if we were to think about this points ordered pair, the x value would have a number, but the y value is specifically and always 0. On the other hand, if we look at a y-intercept, any point on the y-axis, the x value is always 0, but the y value will be a number. So something special about these x and y intercepts, the y-intercept will always have an x value of 0, and the x-intercept will always have a y value of 0. So we can use those two big ideas to help us find the x and y intercepts of these examples. Now these are the same three examples as before. Okay, so we already found the domains of these three examples. Now we're going to find the x and y intercepts. So maybe let's find, I don't know, we'll do the y-intercept first. Okay, so to find the y-intercept, the x value is always 0. So if we know the x value is 0, let's put 0 in for all of our x's. Simple substitution. We'll put in 0 for all of our x's. Y equals 0 minus 4 is negative 4. And then we have 0 squared is 0 times 2 is 0. Negative 8 times 0 is 0, but 0 and a 0 give us 0, so we're left with negative 4 over 0. So this is undefined. Okay, we can't divide by 0. We know that. That's how we find a domain. So there are no y-intercepts in this case. Okay, we kind of get an undefined answer. There's no y-intercept. But now let's try to focus on the x-intercept. So in this case, the y value is 0, so we can put 0 in for our y position, and we're left with x minus 4 up top, and then a 2x squared minus 8x in our denominator. Now this is where it gets a little bit tricky because we got x's all over the place. We want to figure out what is the x-intercept, but this is actually pretty simple when we take the time to take a look at what this is actually telling us. We have a fraction specifically equal to 0. Okay, we know the answer to this fraction is 0. Now if we think about that, what kind of fractions give us an answer of 0? Okay, well maybe we can do 0 over 2. 0 divided by 2 definitely gives us an answer of 0. If I tried another one, 0 over negative 100 would still give us an answer of 0. So if we specifically know our fraction equals 0, we definitely know that the numerator, okay, the top piece must equal 0 in order for the entire fraction to equal 0. So let's just focus on the top piece here. We can have 0 equals x minus 4 because we're only concerned with the top piece. That's what we know equals 0. So our x solution in this case would be 4. So our y-intercept is 4. Now we can write that as an ordered pair. We can write it as 4, 0 if you wanted to. So just to kind of recap, okay, if we go back to the domain, notice how we were focusing over here when the denominator equals 0. Okay, that's finding the domain. But when we're finding an x-intercept, we want the top to be 0. So we're still focusing on our fraction. Different pieces are going to equal 0, but depending on which one you're focusing on, you're finding something different. If the top is 0, that's an x-intercept. If the denominator is 0, you're finding the domain. So we really got to try to keep those two pieces separate because they are very similar. Alright, let's check out the next one. Maybe we'll find our y-intercept. Simply plug in 0 for our x's. Maybe we can do this in our heads. This would be 0, this would be 0, and this would be 0. So all of these would cancel because they're essentially zeros. And we're left with negative 3 over 4. So our y-intercept is 0, negative 3 over 4. A little shortcut there. Now to find our x-intercept, when the top equals 0. So we have 0 equals 6x squared plus 7x minus 3. Okay, we don't care about the bottom, that's just finding the domain. Okay, the x-intercepts are focusing on the top. So our little squared here is cluing us into factoring. 6 times negative 3 gives us a negative 18, but we want to add to 7. So two numbers that multiply to negative 18, but add to 7 are, what do we have? I think we would have a positive 9 and then a negative 2. So then when we divide by 6, 9 over 6 simplifies to 3 over 2, but we can move the 2 out as a coefficient. Negative 2 over 6 simplifies to negative 1 over 3, but we can move the 3 over as a coefficient as well. So we have two solutions for our x-intercepts. X would be negative 3 over 2, but also a 1/3. So we could write those as ordered pairs, negative 3 over 2, comma 0, and 1/3, comma 0. So in this case, we actually have two x-intercepts. All right, moving on. For our y-intercept, we can simply substitute in 0 for our x's, which means those go away. So we're left with 5 over 1, which is just 5. So our y-intercept would be 5. Now for our x-intercept, we're focusing on when our top piece equals 0. And if we were to solve, negative 5 equals x squared. Square root of both sides is plus or minus I square root of 5. But notice how this is an imaginary number. Okay, it doesn't exist on our coordinate plane. So we have no x-intercepts. Alright, the next thing we can find are those horizontal asymptotes. Now we know how to find the vertical asymptotes. Those come from our denominators, like when we cannot remove a specific factor, but we do have kind of a quick way to help us find horizontal asymptotes. And we're specifically looking at the degree, or in other words, the largest exponents in our equation, or in other words, the largest exponent of the numerator, as well as the largest exponent in the denominator. So we do have three little rules here that we kind of just have to know to help us find horizontal asymptotes, but these will be our shortcuts. So if we have an example where the degree in the numerator is bigger than the denominator, okay, we're always comparing numerator and denominator. If the degree in the numerator is bigger, then we don't have any horizontal asymptotes, okay? We're not going to have any dotted lines going across our graph, meaning left and right. But if the degree in the denominator is bigger, okay, so if the numerator is bigger, we don't have any asymptotes. But if the denominator is bigger, we do have a horizontal asymptote, and it's specifically always going to be y equals 0, or in other words, that x-axis. So depending on which part of your fraction has the larger exponent, one of these two pieces will be true about your graph. But sometimes the degrees of the numerator and the denominator are the same. So this is where it's a little bit different. We're going to divide the coefficients of the degree terms. So we're going to have three examples down here. Notice how they're the same exact three that we've been dealing with. We've already found the domain of these examples. We've already found the x and y intercepts of these examples. Now we're going to find the horizontal asymptotes. Do we have any? Is it at the x-axis? Or do we have to divide some coefficients to find out exactly where it is? So let's take a look at our first example. The degree of our numerator is 1. Okay, that's the largest power on the x. The degree in the denominator is 2. It looks like our denominator is larger than our numerator. Okay, 2 is bigger than 1. So in this particular example, we're going to have a horizontal asymptote at the x-axis. So we can say there's a horizontal asymptote at y equals 0, or you could say x-axis, whichever one you prefer. Taking a look at this one, the degree of the numerator is 2. The degree of the denominator is 2. Okay, so those are the same. So we're specifically having a horizontal asymptote, but it's going to be at the division of our coefficients of the degree terms. So that means, notice how this 2 was a degree. The coefficient on this term is 6. And then we divide that, just like we have in our problem, we have a fraction. We divide by the coefficient of the denominator's degree term, which would be a 1. So 6 divided by 1 gives us 6. So in this example, just to give you a little picture, we're going to have a horizontal asymptote specifically at the x-axis. So we could draw one right here. But in this case, our horizontal asymptote is up a little bit. It's specifically at a y value of 6. We would be able to draw one somewhere up here. Okay, that's the difference between these two. This one is always at the x-axis since the bottom is bigger than the top, but in this case, since they're the same, we can find a more specific value where the horizontal asymptote would be. Now for our last one, the degree of the top, or our numerator, is 2. The degree of our denominator is 1. The numerator is bigger than the denominator, so we don't have any horizontal asymptotes. Okay, no HAs. Alright, so we're going to focus on this last one just a little bit further in our next example. Okay, so notice how this one did not have any horizontal asymptotes. There is no horizontal dotted line on our graph. But this graph, or this specific equation, might have what's called a slant asymptote, or in other words, an oblique. If you think about on your body, the oblique is on the side of your stomach, kind of on your waist, and when you see someone that's really fit, kind of really buff, I guess you could say, you could see the obliques on their abdomen, how they're kind of at a diagonal. So we call these slant or oblique asymptotes because they're not always, or they're not horizontal, they're not just going straight across, they are going to be angled a little bit, or either going up or going down. So we can have these slant asymptotes. Now there is a slant asymptote when the degree of the numerator is greater than the degree of the denominator. So that's exactly what we have here. The degree of the numerator is larger than the degree of the denominator. So it doesn't have any horizontal asymptotes, but it will have a slant asymptote. So in order to find a slant asymptote, with kind of these diagonal lines, we're going to perform long division to find it. So in this example, we're taking our x squared plus 0x plus 5. Okay, if we're doing division, we need the placeholders, and we're dividing it by x plus 1. So if we go through our little process here, x squared divided by x is just x. We can multiply that over and subtract. First terms cancel. 0 minus 1 is negative 1x, and we can bring down the 5. Negative x divided by x is negative 1. We can multiply that over and subtract. So first terms cancel, and we're left with 5 minus negative 1, which changes to a plus 1, so we get a 6. So we're going to ignore the remainder. We don't worry about this. But this guy right here, our quotient, is the equation of our slant asymptote. So we can say we have a slant asymptote specifically when y equals x minus 1. And we can graph that. Okay, this is our b value. So if we thought about a graph, we could plot negative 1 right here. And with our slope, we can go up 1 over 1, up 1 over 1, up 1 over 1. And since this is an asymptote, we have this dotted line going across our graph. So we might have a graph that, I don't know, looks something like this. Okay, if it's an asymptote, your graph is not really crossing it or touching it, it just approaches it. So we do have this slant asymptote. It's not horizontal, it's not vertical, it's slanted. Okay, and we can find that slant asymptote by using the long division process. Alright, so let's try to put everything together and graph these 3 rational equations that we've been kind of going through with all of our different examples. We're actually going to take all the information that we found and plot it to help us graph this equation. So some things that we've already discovered about our first example here, x cannot equal 4 because it's a whole. We found that out with a domain. We also found that x cannot equal 0 from the domain. It's specifically going to be a vertical asymptote. I want to focus on this one for a second. Okay, we've actually found an x-intercept to be 4, 0. But take a look at what this is telling us. Okay, specifically, we have an x value of 4. But notice how here, when we found the domain, we said x cannot equal 4. This is a whole. So even though this is an x-intercept, it should be an open circle. Okay, an open circle because the x value of 4 cannot exist. So we know this is where our graph should kind of be, but it's not actually going through this x point right here, this 4, 0, because it's specifically a whole. So you got to check out all this information and really analyze it. Try to figure out, are there any pieces that are missing? What is all of this telling me? Now we also found that there's no y-intercept, and we specifically have a horizontal asymptote when y is 0. So let's kind of plot all this information. X cannot equal 4. Okay, there's a hole there, but it's specifically here, so we can put a little hole there at 4, 0. We have a vertical asymptote when x is 0, so we can put a vertical asymptote dotted line at that x value. We also have a no y-intercept, so we can't put a dot there. We also have a horizontal asymptote going across at 0. And that's all that we basically have. Okay, so based on this information, we're kind of getting a general layout about what's happening on our graph. Now, to figure out the rest of the pieces, this is where your graphing calculator is going to help you out. So let's bring up our graphing calculator. We can type in our original problem into our calculator. Make sure that your window matches the grid that you are drawing your graph on. So this is going from -10 to 10 in both directions, so we can write that there. And then we're going to hit graph just to give us the general shape, but we know that it should be kind of bound between these asymptotes and this hole. So based on this picture, we have this little curve in the top right-hand piece, as well as the little curve in the bottom left-hand piece. So if we were to put all of that together, we have this piece here. Okay, there's a hole. We got to go through that. We don't have a graph there. And then we have this piece here as well. So there's our graph. We're using the information we found on it by our own or by ourselves, and we're plotting that on our graph, but then we're going to use our calculator to help us give us our final shape. Alright, moving on to our next example. For this particular equation, throughout the lesson, we discovered how it has a domain of all real numbers, so every single x value is going to work. We specifically have x-intercepts at -3/2, which is just -1.5, so we can put that there. And we also have one at 1/3, so we can put that there. And we also have a y-intercept at -3/4, so that's not quite 1. We can put that right there. And a horizontal asymptote at 6. So drawing our horizontal line at our y value of 6, somewhere right there. Alright, so we know our graph is specifically going to go through these points, but it's going to approach this line up here somehow. So let's go to our graphing calculator and see what we get. Alright, bringing it up, we can type it into our graphing calculator. Make sure that your window matches the grid or graph you're drawing on. And when we hit graph, let's see what happens. Alright, so notice how it's kind of leveling off at 6 up here, and we come down, go through our x-intercept, then our y-intercept, and then our x-intercept. So if we just try to mimic what our calculator looks like, going through those specific points, coming back up, and then leveling off again, there is the graph of our rational function. Alright, last but not least, let's check out our third example. All the information we found out about this example is over here. We said that x cannot equal -1 based on the domain, so we have a vertical asymptote when x is, not +1. We want to make sure that's -1. So that's over here. Okay, big difference. We also found that there's no x-intercept, so we don't have to worry about plotting a dot there. We do have a y-intercept at 5, so we can put a dot there. No horizontal asymptote, but this one did have a slant asymptote, so we got to plot or graph the slant asymptote. We begin at -1, somewhere down here, and we go up 1 over 1, up 1 over 1 based on the slope. So we could draw our slant asymptote appropriately, looking something like that, and we could go in the other direction as well. So there's our slant or oblique asymptote. So we're going to be bound, our graph's going to be bound between these asymptotes somehow, but it's specifically going to go through this particular point. We can use our graphing calculator to help it, or help us do the rest, just to get a basic picture. And it looks like we're going to be down here in this little piece, and then up here as well. So if we try to copy this the best we can, looks like it's trapped right in there. and specifically going through that y-intercept, but then comes right back up. Because of those asymptotes, they're not going to touch it. We're just going to approach it. Alright, so let's try to graph a rational equation from the very beginning, trying to find all that important information and then graphing it. So here is our rational equation. First thing we want to do is find any holes or vertical asymptotes. In other words, that's finding our domain. So let's try to factor as much as we can to help us find the domain and maybe even some of these other pieces. Taking a look at the top, we can take out an x, and we're left with 2x squared minus x minus 1. And factoring the denominator, two numbers that multiply to 1 but add to 2 are an x plus 1 and an x plus 1. Now we can factor the numerator a little bit further. That would factor as a 2x plus 1 and then an x minus 1. But if we take a look at our overall factors right now, it doesn't look like anything's going to cancel out. So we don't have any holes, so we could write none. But we should check for vertical asymptotes. In our denominator, what values for x will not work? Clearly that is -1. So let's go right ahead and just plot that right now. We have a vertical asymptote at -1. We can draw that on our graph. Alright, moving on to our y-intercepts. Remember, that's when we have an x value of 0. So if we plug in 0 for all of our x's, the tops are going to disappear and part of the bottoms are going to disappear. So all the numerator is gone, we're left with 0. In our denominator, we're left with a 1. So our overall y-intercept is just 0. We could write that as an ordered pair and plot it. Now taking a look at our x-intercepts, that means we have a y value of 0. So y equals 0, and we're specifically looking at our numerator for this piece. Because if our overall fraction equals 0, then just our numerator equals 0. And we're going to have multiple x-intercepts. This x is giving us an x-intercept at 0. This x is giving us 1 at -1/2. And this x is giving us an x-intercept at 1. So let's plot those. X-intercept of 0 is already plotted. That's at the origin. -1/2 is just a little bit right there. And then an x value of 1 right there. Kind of cramped, but that's okay. We can plot that information. Alright, moving on to horizontal or slant asymptotes. This is when we got to take a look at the degree of our equations. In the top piece, our degree is 3. In our bottom piece, the degree is 2. The top is larger than the bottom. So in terms of horizontal asymptotes, that means we don't have any. But we should check for slant asymptotes, and we can perform long division to help us do that. So we can take 2x cubed minus x squared minus x plus 0, we need that placeholder, divided by x squared plus 2x plus 1. So 2x cubed divided by x squared is 2x, and we can multiply that over and subtract. First terms cancel. -1 minus 4 is a -5x squared. -1 minus 2 is -3x. And we can bring down the 0 if we want to. Moving on, we can do -5x squared divided by x squared. That just gives us a -5. Multiplying it over, we have -5x squared minus 10x minus 5. And subtracting gives us, first terms cancel, then we're left with a 7x. Remember, subtracting a negative changes this to a positive. And 0 minus -5 again changes to a positive 5. But with the slant asymptotes, we're not really concerned with the remainder. We're just focusing on our quotient. So our slant asymptote is y equals 2x minus 5. So let's actually plot or graph that slant asymptote. Down here at -5, we can go up 2 over 1, up 2 over 1. So if we were to draw in our slant asymptote, looks like it would be something like this. Alright, so from here that we graphed everything we know about this rational equation, we can use our calculator to help us fill in the rest of it. So bringing up our calculator, typing in our example, we can hit graph. Alright, let's take a look at this. It looks like, okay, we have the vertical asymptote right here. So it's going to come up right here at the vertical asymptote. It's going to go through all these points. So it goes through that x-intercept, through that y, or another x and y-intercept, then through this one, so it kind of has this hump thing going on. But as it continues, notice how it's approaching the slant asymptote. Okay, so it's kind of going off at an angle. It's not leveling off horizontally like a horizontal asymptote would. So if we fill in that piece, we come up here from our vertical asymptote, through the x-intercept, through the y-intercept, through another x-intercept, and then it levels off on a diagonal from our slant asymptote. Alright, so what I want you to do is pause the video and try this one on your own. From the very beginning, I want you to find all these critical pieces of information about our function and then graph it. Alright, so let's check it out and see how we did. Factoring our rational equation, it looks like we can cancel out some factors of x plus 2. So if we can cancel those out, that means we have a whole at an x value of -2. But in terms of vertical asymptotes, we are left with an x plus 6 in the x plus 3 in the denominator. So we would have a horizontal asymptote of x equals -3. So we can put that on our graph right there. I'm going to hold off on the whole for a second. I'm going to show you how you can draw that in on your graph. Y-intercept, we can put 0 in for all of our x's, which means these go away. We're left with a -12/6, which just simplifies to a -2. For our x-intercept, our y value is 0, so we're specifically just looking at the numerator since our overall fraction is 0. Since this is our overall numerator, okay, that's what we get at the end after we simplify it, we can simply add 6 over, so we have an x-intercept at 6 equals 0. So, moving on to horizontal asymptotes, we got to take a look at the degree. The degree of the top is 2, the degree of the bottom is 2. They're exactly the same. So we got to take the ratio, or divide the coefficients out front. It looks like we have a 1/1, which just simplifies to an overall horizontal asymptote of 1. So we can draw that in right there horizontally. Here are the intercepts, by the way. We can plot those. Since we have a horizontal asymptote, that means we're not going to have a slant one. So with all this information, we can plug this into our calculator and have it help us draw the rest. Alright, so it looks like we have a piece on the left-hand side, so somewhere over here, and our other piece is in the bottom right-hand side, specifically going through the intercept, looks like right there, as well as this one kind of right there. So if we draw that in, there's our first piece, and there's our second one. But we got to be careful because we said we had a whole. So right here, when x is -2, this is kind of going to be tedious for us. We need to actually take that piece out and make sure we show the hole that's actually there. So I'm going to draw a little hole right there, so showing how we do not have a piece of our graph right there. So yes, it kind of can be tedious, but it is important because we specifically don't have a piece of our graph when x is -2. Hopefully we did really well with that. Good luck on the practice and the application, and most of all, that mastery check.